Okay, welcome guys to our channel, Maths Bay. Maths Bay, Metric Maths Made Easy. Okay, this is your tutor, Mr. Ntlagani Pongwani. So today we are continuing with our series of basically solving grade 12 problems. Grade 12 problems. And remember that we have started with trigonometry. So we solved some trig identities, and we solved one 3D problem. Right? You can find this. You can find those problems on this channel. So remember to go there, to subscribe, like, comment, and so that you get familiar with our content. So I decided to start with trigonometry and Euclidean geometry because those two topics are the topics that carry most marks, and that also most students find difficulty with, right, here in South Africa. Okay, so but the lecture or this channel is not only targeting South African students, so everyone from around the globe, you can sort of tune in. Maths is maths at the end of the day. Okay, so today we're moving on to Euclidean geometry, and we'll start by proving theorems that are examinable, right? Okay, so the first theorem that we're going to prove today, we're going to try and prove, is the one that says the angle between a tangent and the chord is equal to the angle in the alternate segment, right? Angle between a tangent and the chord is equal to the angle in the alternate segment. Put differently, the angle between the chord and the tangent is equal to the angle subtended by the tangent in the circle, right? So if you look at this diagram here, the chord is AB. So this is the chord AB. So the angle between the tangent is XBY. So the angle between the chord and the AB is this one here. I'm just marking it. So it's angle XBA. So, and then if you move from the ends of this chord, so that's what subtending means. So if you move from the ends of this chord like this, and then you converge at the circumference of this circle, so the angle that is formed there, so that's angle C, is equal to angle XBA. So that's what we're trying to show, right? Trying to show that angle XBA is equal to angle C. So when you're trying to prove something like this, you make use of the theorems that you already know, right? Okay, good. And also when you are doing some proofs of this nature, there will always be lines that are already there but that are not visible. So in your attempt proving what you are required to prove, you need to construct certain lines so that your point will be more visible, right? Okay, so that's what we're going to do. And also you should always know why you're constructing the lines you're constructing. So we're going to try and move away from the habit of memorizing proofs towards actually understanding them, why we're doing what we're doing. Okay, so the first step is to construct OA and OB. So that's what we're gonna do first, right? Construct OA and OB. Remember that point O is the center of our circle. So OA is a dotted line. We use a dotted line to show that this is the line that we've constructed ourselves. So, and then OB, you just drop. So that's the line that goes to the tangent. So a tangent is the line that touches the circle at only one point. So XBY touches the circle at point B only. So the line that we've constructed is OA and OB. So what are these lines? Because they are from the center to the circumference. So these are your radii, right? So OA is equal to OB because they're both radii. So OA is a radius and OB is a radius. So you have to know why you constructed these lines. So you constructed these lines so you will have triangle AOB. And once you have that triangle AOB, and since we're talking about angles here, we're trying to show that this angle is equal to that angle there. It means that you must know the interior angles in your mind. At the back of your mind, you must know that you need to basically find the interior angles of triangle AOB. So this angle here, that angle there, and that angle there. So these are the angles that you want. I'm just going to put dots. If I had a different writing pen, I would actually mark the angle. So those are the angles that you want. Right, okay. Okay, so I think earlier I've already said that when you are doing these types of problems, you use the theorems that you already know. So we know that if you drop, I'm going to try to make this more visible. Okay. So we know that if you drop a radius and if you drop radius OB to line XBY, the angle that OB makes with XBY, with line XBY is 90 degrees. Okay, because the radius is always perpendicular to the tangent, right? So the radius is perpendicular to the tangent at a point. So if our radius comes to point B, the tangent that you will draw at point B will make an angle 90 degrees with the tangent. So we can just go ahead and write that. So we can say angle OBX is equal to angle OBX is equal to 90 degrees. And then our reason will be radius perpendicular to the tangent. That's enough. Okay. So angle OBX, this is angle OBX, so that's the angle between the tangent and the radius. So that angle there is 90 degrees, angle OBX, okay? So remember that the main thing that we want is the interior angle of triangle AOB. So we are basically looking for OB, angle OBA. So this angle here, because it's the first one we can get straight away, right? Or right away. So we know that if you look at these angles, so we have this angle that we've indicated here, and also we have this angle. We've just shown that these two angles, they make up angle OBX, and angle OBX is equal to 90 degrees. So we can actually write that down, that angle XBA plus angle OBA is equal to 90 degrees because they are equal to angle OBX. So we can just say angle XBA plus angle OBA is equal to angle OBX. x. That's just what it is. So this angle plus this angle, they make up this whole angle. But we've just shown that angle OBX is 90 degrees. So therefore angle XPA plus angle OBA is equal to 90 degrees. So now remember that our intent is to get the angle that is interior to triangle AOB. So we need to make angle OBA the subject of the formula here. So angle OBA is equal to 90 degrees minus angle XBA. Okay, so we are happy now because we have one angle that's within triangle AOB that we know. So we know that it's 90 degrees, angle OBA is 90 degrees minus angle XBA. So now we can use the fact that line OA is equal to line OB, because that implies that angle OBA is equal to angle BAO. Remember that we must try by all means to get all angles of triangle AOB. So we say angle BAO is equal to angle OBA. So the reason is base angles of triangle AOB are equal. Base angles of triangle AOB are equal since OA is equal to OB. Or you could just say base angles of an isosceles triangle are equal, right? So I said base angles of triangle AOB are equal since OA is equal to OB. So that justifies me saying angle OBA, angle BAO. So this angle here is equal to angle OBA. So that means angle BAO is equal to 90 degrees minus angle XBA, right? Angle BAO is also equal to 90 degrees minus angle XBA. Remember that our goal is to get all angles of triangle AOB. Why do we want to know the triangles of the angles within triangle AOB? It's because we're gonna use the theorem that speaks about the angle subtended at the center in relation to the angle subtended at the circumference by the same chord or by the same arc, right? So ultimately we want to know angle AOB so that we can relate it with angle C. You understand? Okay, so since we know these two angles, since we know this angle and that angle, we can easily get that one using the sum of angles within the triangle. So if we say angle OBA plus angle BAO plus angle AOB is equal to 180 degrees, and then we provide our reasoning that sum of angles of triangle AOB, right? So we know that but angle OBA is equal to angle BAO. So this is angle OBA plus angle OBA plus angle AOB equals to 180 degrees. So we've just changed angle BAO into angle OBA, because remember we've shown that angle BAO is equals to angle OBA. So we have angle AOB equals to 180 degrees minus 2 times angle OBA, right? Because angle OBA plus angle OBA, that's 2 angle OBA plus angle AOB. And then when we're solving for angle AOB, we let 2 angle OBA go to the other side and we change the sign. So angle AOB is equal to 180 degrees minus 2 times angle OAB. Now we just substitute. So 180 degrees minus 2 into, remember that angle OBA is 90 degrees minus angle XBA. So we write 90 degrees minus angle XBA. So this comes to 180 degrees, negative times positive, negative 180 degrees, negative times negative, positive 2 times angle XBA, right? So we therefore have angle AOB is equal to 2 times angle XBA, right? So we've just used the fact that the interior angles of triangle AOB add up to 180 degrees, and we use that to our advantage to get angle AOB. Now we're going to use the theorem that says the angle subtended by the arc AB at the center is twice the angle subtended by the same arc at the circle. Remember that we already have angle AOB in terms of the angle XBA that we want, and now we're relating it with angle C. So we then say angle AOB is equal to 2 times angle C. So our reason is angle at center is equal to 2 times angle at circle. Yeah, I thought I cheated there, but no, I can use that theorem. Okay, so angle AOB, we've just shown that it's equal to 2 times angle XBA. So 2 angle XBA is equal to 2 times angle C, right? Therefore, angle XBA is equal to angle C. So angle XBA is equal to angle C. So angle XBA, so this angle here is equal to that angle here. Voila, we've actually shown. We've proved that the angle between the chord and the tangent is equal to the angle in the alternate segment, or angle subtended by that chord in the circumference. Okay, so I hope you understood the procedure. It wasn't complicated at all, and you understood why we had to construct the lines that we constructed. We had to construct the lines that we constructed, and how we actually made use of them. So please subscribe, like, comment, and make this your home. Thank you. Bye.